What's up, guys? So by popular request, here is a little take-up video on the comp mock test. Alright, let's go. Let's start with question 1. So it's asking you to determine whether the following is a tautology, contingency, or contradiction, and we can use logical equivalencies or a truth table. So let's just use both. Alright, so first I'm going to do a truth table. I have two variables here. I have A and B, so I'm going to write out the truth table for that. Okay, and since I'm going to need a not B later, I'm going to write down the not B as well. So that's false, true, false, and true. Cool. So now let's start off with the inside part first, because it'll be easier to start from there. So I'm gonna first do A and not B. Okay, so A and not B. So we know that both of them have to be true for A and not B to be true. So first is true and false, so that means this is false. This is true and true, so it's true. This is false and false, which is false. And this is false and true, so that's a false. Cool. So now I have to do A and B ORed with B. So I'm just going to call this C to make it a little easier to read. So that becomes C or B. And now we look at this column and we OR them together. And for OR, we just know that one of them have to be true for the entire statement to be true. So let's do this. First is true and false, so this is true. Next is false and true, so this is true. This is true and false, so this is also true. This is false and false, so this is false. Okay, I'm going to call this D now, because now we have to do it. A has to imply this whole part of the equation. So let's call that D just to make it easier to read. A implies D. So now we look at column A and we look at column D. And for implication to be false, a truth has to be implying a false. So anything else is true. So let's go through this. First we have a true implying a true. This is a true. We have a true implying a true. Again, this is true. Now we have a false implying a true. This is true. And a false implying a false is also true. So by truth table, we have proven this is a tautology. Alright, so now I want to show the same thing using logical equivalencies. So let me just copy this question over so you don't have to waste time writing. Okay. So let's just get right into it. So when we're trying to prove something's a tautology, contingency, and whatnot, we know that something has to be true or we have to reduce it down to a true or false, right? So, and the only way we can reduce stuff down using true and falses is using and or. So let's use the implication relation here so that we can change this to a not A or A and not B or B. Okay, this is the implication relation that I used here. And next step, remember three equivalents, whatever that word is. Yes, three dashes. Alright, so next step, I look here, and if you refer to your rules, this looks very similar to the distributive law, so let's do a distributive law on this. So we have B or A first, right? Let's write that down as A or B, and that's ANDed together with a B or not B. To be or not to be, ha ha ha, no, okay. Distributive is what we used here. Okay, so next line. We know that we can reduce this down to a true. So this is not A or B and true. I forgot the name for this one. but if you look on your table, you'll see that this is a true state. This will return a true statement. Okay. Next, we can actually use this whole statement as something. So I forget the name of it as well, but whenever you have a true ANDed with something, we know that the result is always going to be this statement. So when you have a not a or, and then we have not a or, and then we have this statement ANDed with the true, so this just becomes A or B. Again, please refer to your tables because I can't have it on the side over here, and I apologize for that. And next step, I just want to get rid of these brackets, so I believe that's just the associative law being reversed there. And then now I see I have a not A or A, and that becomes a true. And whenever you have a true ORed with something, we know that it's always going to be true. So this is a true statement, and we have proven both ways it's a tautology. Alright, so now let's take a look at question 2. So question 2, it's asking us, it's given us a universe of discourse of all animals. So let's use that as a universe of discourse. So this is all animals. Okay, and it's saying let L of x be, x is a lion, so L of x equals x is a lion. And then we have M of x, and it says x eats meat. And then you have G of x, which says x eats fruits. Cool. Alright. So now it's saying state this statement logically. So it says all lions eat meat and some lions do not eat fruit. Okay, so let's put this out logically. So right here we see we have an all and a some. So we know we're going to be using our universal quantifiers of all and some. Alright? And we see here we have lions eat meat. Remember, this is important because our universe of discourse is all animals. We have to state somehow that there are lions and they eat meat. Okay? So let's first look at this part, and it says all lions. So all lions, so that's going to be, we're going to have to use our universe of discourse of all animals because we haven't got a specific one at the moment. So it says for all x, we have lions, so we have to state that it is a lion, so we have to use L of x, right? And we also have to state that it also eats meat, so we also have to say it's eats meat like that, right? And now it also says and some lions, so we have an and connecting our two statements together, and we also have, now we have some lions. So we have some lions, so we also have to state again that this is a lion, so we have to use L of x. And then we also and this together and say that they do not eat fruit. So we can just negate our predicate here, and that becomes the logical statement for this statement. It's a fairly easy question. Just remember, if you don't have a universe of discourse of just lions, then you have to remember to keep this statement with it, right? Because this is the only thing that states that it's a lion. So just remember to keep that in there and you'll be fine. So moving on to question 3 now. This one's fairly simple. So it's just saying determine if the following statement is true or false. So it says if 7 is less than 3 or 3 plus 3 equals 6, then 4 less than 4 is less than 8, and 3 equals 5. So we see the if then right here, so we know there's going to be an implication. And we also see there's a or here and here. So basically what we have is a or that's implying a and. That's the wrong symbol for or. Okay, so now first we have to determine if the or is true. So we know that 7 is less than 13, that is true. And 3 plus 3 equals 6, so this whole or is true, right? And then 4 is less than 8, and 3 is equal to 5. So 4 is less than 8, that's true, but 3 does not equal 5. So this statement is false because this is two truths, so when two truths are ORed together it's a true, but here we have a true and false, and when those are ANDed together it's a false. So now we have a true and a false implying a false, true implying a false, and we know that when a true implies a false, this is a false. So, I mean, if you want to write that out in words, you can, but that's, the statement is false because of these reasons. Okay, so now we have to, we'll move on to question 4 now. So state the inverse, converse, contrapositive, and the contrapositive of the following implication. So the inverse, we know that it is the not A or not B. It's just basically this equation is A implies B. And we know it's A implies B because it says the if then right here. So we know it's an implication. So we can call this statement here A and this statement here B. Okay? And so now the inverse, converse, and contrapositive, they're in your notes. You'll be able to find them. So we know that the inverse is not A implies not B. The converse is, sorry, I gotta look up a sec. B implies A, and the contrapositive is not B implies not A. Okay, so first I'm going to write out the inverse. So if we look here, we have not A as our first one. So say we called this first statement here D, and this one here F. Okay, so we have a D or F, right? And that whole thing is going to be negated, right? So when you distribute a negation into there, you're going to end up getting, so I'm going to move the answer up here, not D and not F. So we can write that out in words. If the network is slow and the firewall is up, then, okay, let's look at the second part here. The server accepts connections. Well, we need the not of that, so we just write the server does not accept connections. Alright, so next we're going to look at the converse. So that's basically just we're flipping the statements, so that's pretty easy. So let's write that out. If the server accepts connections, then the network is not slow firewall is not up. Cool. So now let's finally look at the contrapositive here. So the contrapositive asks for not B implies not A. So we know that not B is if the server does not accept connections, then now we look at the not A, which is pretty much the same as this one. It's exactly the same as that one. So the network is slow and the firewall is up. Cool. And that's how you do question 4.